Do people know what I mean by post-quantum crypto? Good, because I don't have a slide on that. And nobody's, the other question is, how many people are expecting me to go into the math and the internals of the post-quantum algorithms? Okay, I'm not doing that either. I do have another talk on that, but okay. So I'm Bob Relyea. I'm a longtime NSS developer. Been doing it since 1996. My career started at IBM, and then I went to Netscape, iPlanet, and from Netscape on to iPlanet, AOL, and Red Hat, which is now owned by IBM, so I'm back at IBM. I've been doing this, working on the same code base. That's all NSS work by those other companies. I'm currently part of the Red Hat team that does crypto. I'm responsible for the NSS part, but the team is responsible for NSS, OpenSSL, GNU TLS, and indirectly responsible for all the crypto. So if you do crypto, our team wants to know about it and usually tell us, you need to use one of these libraries. My other hat is I'm the co-chair of the PKCS 11 OASIS technical committee. Okay, so we want to implement post-quantum as a PK11 algorithm. So what are some of the unique issues that we have with post-quantum? The first one is that the post-quantum uses new primitives in order to do key exchange. KEMS are pretty much sort of brand new, and all of the new key exchange algorithms are planning on using KEMS. The other major issue that we have is many of the new signature algorithms contain things in the signature that you need before you start hashing. And so now we need to be able to, we need to have the signature at the beginning of doing hash functions instead of at the end. They've also added contexts to signatures, which are sort of random data that gets incorporated in the hash somewhere that is used to distinguish your use of the signature versus some other use. So you can say, I'm hashing for SSH, and now that signature is only good for SSH. And when you verify, you need to use the context string for SSH. There's also, I'll go over hedge and deterministic a little later. And another issue is these private keys are generated by seeds. And these seeds weren't part of the original spec. They were just code in the spec. But a number of vendors, particularly people who need to store a lot of these keys, wanted to store them as the seeds because they're smaller than the actual expanded key. And so that's caused some interesting issues that we have to deal with. OK, key exchanges. So here's our classic sets. The first two are our classic sets of key exchanges. You're probably familiar with KEA. You take your public key, you take the key you want to send, you encrypt it, you get ciphertext, and then you decrypt it by adding the ciphertext with the private key, and you get the original key back. KEX is your typical DH and ECDH, where you take two key pairs together, and then you run an algorithm, and you wind against your public key and your partner's public key, and he does the same thing with your public key and his private key, and you wind up with the same key. KEM is an attempt to be able to bring those two together into one algorithm. So in KEM, you start with the public key, and you run a command called encapsulate. Encapsulate will return you two things, a ciphertext and a key. On the other side, you do a decapsulate with your private key and the ciphertext that was generated from the encapsulate operation, and it'll return you the same key that encapsulate returns. In general, you can turn a KEA into a KEM. You can turn a KEX into a KEM. Turns out you can turn a KEX into a KEA, and you can actually turn a KEM into a KEA. It's important that you can do these different things because actual ML KEM is actually a KEX turned into a KEA turned into a KEM. The other thing that you cannot do is you can't turn a KEM or KEA into a KEX, and this is causing problems with protocols that are highly dependent on KEX and KEM. Here's how you do KEA to KEM. That's more of a, you can go download my slides later and review that. Here's how you do KEX to KEM. And here's how you do a KEX to KEA, which sometimes isn't quite as obvious. You end up generating the KEX key, and you use that key to XOR the key that you want to encrypt. Or you can also at that step do actual like AES encryption or something. And then you pass both the public key and the encryption key, and then on the decrypt you split those two things out. Okay, signatures. What are the challenges we have on signatures? As I mentioned, the new post-quantums have built-in context, so we need to figure out how to pass those in as signatures. In MLDSA, there's a random hedge factor that are used to make the signatures not the same through multiple calls. Sometimes you don't want that. If you're hashing the same data, you want the exact same bits for the signature. So they have a deterministic variant that replaces the hedge value from being a random value to being something that's generated, so that you will always get the same signature. And different applications will need one or the other of those. The other one is what I mentioned before. SLDHA and FNDSA and HSS and XMSS have this value in the signature that you need before you start hashing. So we need variants at verification step that starts with the signature at the very beginning. Okay, challenges to actually implementing PQ. It's very, very tricky to actually implement these new algorithms. The biggest issue is their side channel issues with lattices and most of these other algorithms. And these side channel issues make the issues that we have with ECC and RSA look extremely straightforward. So if you've been out here and implemented ECC or RSA, Alicia has probably broken your algorithm showing how it's not side channel safe. Lattice has a bunch more holes that you can poke at, and he's now busy, or she's now busy poking at all those implementations that are out there. You don't want to be implementing your own for that. So if you want post-quantum and you're just an application, you go over and use your favorite crypto library. OpenSSL, NSS, and GNU-TLS either has or will soon have these post-quantum algorithms in them, and that's where you want to get them. If, as this talk is, you're a library that's building a PKCS 11 module, well, those PKCS 11 modules are used by these libraries, and so you can't really use NSS because it will create a feedback loop. So what can you do? One is you could use a standard PQ library that exists out there that's a separate library, like liboqs or crux. Or you can pull a snapshot of the sources and then keep that up to date as problems and updates come from upstream. Or you can do a fork on one of those things. Those are really your best three options. And OpenSSL, NSS, and GNU-TLS are actually using either one of those three options for their implementations. None of them have rolled their own actual side channel, their own implementations, because we have some nice, clean implementations that are side channel safe. Never, ever, ever try to deploy the reference information, especially if you haven't hardened it. Those things are created just to show you how the algorithm kind of works. You can use them to generate text vectors, but you do not want to deploy any of them. And never, ever, ever, ever make your own implementation. Okay. Okay, so how do you get this into PKCS 11, the part of the talk? Well, one way, PKCS 11 has some well-defined ways of creating vendors extensions. You can create new functions. You can add new attributes and mechanisms that are in a space that's guaranteed not to collide with PKCS 11 called the vendor space. And in fact, NSS has done this to get PQ in before the NSS spec, and the qubit people have done that in order to make their stuff all work with through PKCS 11 interfaces without having the full PKCS 11 spec that gives us the support. The downside is your PKCS 11 module will only work with software that understands your vendor-specific IDs and won't be general. In NSS, we isolate the applications from that because we actually have if you want to do encapsulate or decapsulate, there's an NSS call that will say encapsulate, decapsulate, and it hides all the PKCS 11-ness underneath that so that you can just call that function and that will continue to work when new PKCS 11 3.2 comes out. And that's the main point of my thing is PKCS 11 3.2 is kind of here. It has been approved as a committee draft, and we're still trying to get it pushed out for public review. It makes a bunch of changes we need for post-quantum. It adds new functions for encapsulate, decapsulate, and verify signature. It creates mechanism IDs for ML-KEM, MLDSA, SLDSA, XMSS, and then it expands the previous definition of HSS to be able to use the verify signature. So the new functions, encapsulate, decapsulate takes exactly what you would expect it to take. Decapsulate actually looks very much like unwrap because it's pretty much an unwrap implementation. The whole verify signature suite, so if you're familiar with PKCS 11, you know it comes in, each of these things come in a init, update, final, and a combination of an update and a final version. So all of those are defined. They look just like the C verify init, except for the init function has the signature at init time, and the verify function does not have the signature coming in at that time. PKCS 11 3.2 says that if you implement the C verify signature suites, you need to implement it for all your signatures that exist already that use C verify signature. But that's extremely easy. You just cache the signature inside your data structure at init time and call your normal verify init. And at the bottom, when verify final is called, you just include that signature. Okay. In addition to those functions, we have some new parameters for the post-quantum signatures. Public and private keys contain CK parameter set. All of the post-quantums use these parameter sets. The values in those parameter sets are algorithm specific and map to those parameter sets that are defined in the NIST spec. But it's a single parameter for all of those keys, so you can have general code that will pull that parameter out at the top of your file and pass it down to code that understands what that meaning is. There's an optional CKA seed on many of the private keys. The CKA seed has that seed value that vendors were trying to use to be able to use the keys in a smaller format. It's optional. You can have either, when you create a key, you can either specify the seed or the value. The downside is tokens are allowed to decide, I don't know how to do seed, I can only take value, or I don't know what to do with value, I can only take seed. If you supply both, you're guaranteed to work. But if your application requires only seed, then you know you need to look at the tokens that only support seed, or that can support seed. The mechanisms. There's a single mechanism defined for ML-KEM, single mechanism defined for MLDSA itself. There's hash versions. and then a single mechanism for SLDHA. The parameter set then determines which one you're going to do. So if you want to do MLChem 55 or MLChem 1024, then you would set that parameter in the parameter list for the key. And when you do an MLChem operation with that key, it will do the MLChem 1024 algorithm. No, we only defined the NIST ones. If you need one of the others, you can ask the committee for them. But we wanted to get the ones that were standardized that we knew people were going to use. Okay, signing. Like the ML KEMS, the param set is part of the signing mechanisms. Deterministic and non-deterministic are done in the mechanism parameter. So PKCS 11, when you do an init with a mechanism, each mechanism has a parameter. Some mechanisms require can do like a null parameter, but mechanisms that need additional information have a mechanism-specific parameter. So MLDSA and SHLDSA have this extra parameter. So it's deterministic decides, you can say either you're doing hedge, which is the standard, or you can say you can say hedge preferred, which is the default, hedge required, which says if you can't do hedge and you're not going to give me a hedge signature, fail, or you can do deterministic required, in which case it will return you a deterministic or fail because it couldn't do it. There's separate between the standard and the prehash versions of the mechanisms. And in the prehash, there's the prehash that you hash it and give it the hash. And there's the prehash where it's doing the hash specifically. So there's a lot of different mechanisms for that, the prehash side. We do not have mu. Does anybody know what mu is? Okay, mu is the standard signature in which the standard signatures hash is done outside. We do not have that support in PKCS 11 3.2. We will add that as a mechanism in 3.3. And we will probably publish that so you don't have to wait till the 3.3 spec is final before you can start using it. Okay, more stuff about prehash. So the mechanism parameters, we talked about hedge. We've talked about, the other thing is this is where the context is. Context is in the mechanism parameters. Now, the mechanism parameters on most of the variants are optional. And if you don't include it, you'll get hedge preference, hedge preferred, and a context of zero length. Okay. So you want to do an actual implementation. Here are the patches I did for NSS from a previous 3.1 token, moving it to 3.2. So the first thing you need to do is you need to create your function list. And this is the standard code for creating function lists. You'll notice that I added a 3.2 only. That 3.2 only doesn't exist in the current spec. But if you add it now, when we do 3.3 or 3.4 or whenever we do update the function table again, that will almost certainly show up with that name. So by doing it now, it means when you get the new header file, you won't suddenly get all these new function lists in your table without breaking, that would break things. So. Okay, and then you just add it to your table along with the other ones. So you can see this is our interface table. We now have the 3.2 function list. You see we have 3.2. We still have 2. And then you also can see these are the vendor-specific ones. This is where we were implementing. You can see a vendor-specific KEM up there. That's where we were implementing KEM. And that still stays around for compatibility in our code. Okay, so I'm in good shape. Okay, talked about the implementing verify signature init. This does not implement the actual verify function for any of the post-quantum algorithms. This is just a function that gives you back the ability to use your existing signature functions with verify signature init. So as you can see, I just call the verify signature, and then I go over and I get the context that's created from it. This is internal NSS. However, you do your internal context would be a little different. I created a new place to stuff it. It's called signature. I just duplicate the signature that comes in and then return. So now I've stuffed the signature in the verify signature content. If this were SLHDSA, I would have a switch at the very top that says, is this one of my algorithms that can't do, that has the signature value in it and needs to start doing it, doing the hash with that signature value immediately. I would have that in there and then branch to the code that I have that does the start of that signature algorithm for the init on that function. So this is where I would start to branch off. But this gives you, you want to do this when you go to PKCS 11, because as soon as you bring your PKCS 11 version 2, you will have this function there, and now people will expect this to work with your existing algorithms. So just to keep RSA working, you need to do this. Verify signature is the hash and then return it function. So it basically checks to make sure it finds the context so that it can then pass it to verify, or finds the signature so it can pass it to verify. Update, really there isn't any different. You can just call the update directly. I actually, in my code, check to see if it has the signature thing and say operation not initialized, so you don't have this case where somebody initializes a verify init and then calls verify signature update, which is just a error in the program. This will help you find those types of errors by returning an error here. And then the final is just like the previous function where we're grabbing the signature and then passing it into the real final. With PKCS 3.2, there's a bunch of other things in that function list that you will have to implement. Well, you will have to have stubs for. And so you will want this, where you just pass CKR function not supported. It's perfectly valid for you to say that these functions aren't supported if you aren't using them. In the current NSS, in fact, all but one of them actually does. This is the actual NSS code except for the get validation flags, because I do have a function that uses the validation flags. And then here's a sample encapsulate. So this isn't like a full implementation. I've ripped out, to fit it on the slide, I've ripped out a bunch of the error checking. But the general idea to do encapsulate is you grab the encapsulation key from CK value, you you grab the parameter set from the public key, you can then figure out the length and make sure that the length is long enough for the ciphertext that you're going to copy in. The create key creates like a blank key that you're going to fill in, and so it takes a template to fill in those values. And then you do the mechanism-specific stuff. So I map the PKCS 11 idea of what the parameter set is to whatever my libraries, underlying crypto libraries parameter set. And then I call the underlying libraries encapsulate, and then copy that ciphertext out, and then set the value in the key, and I'm done, returning the key handle. And decapsulate is actually similar, except I'm using the private key for everything. And in the private key, and I don't have to do a bunch of checks on the ciphertext because I'm not returning it. It's coming in. So it's pretty much similar. OK. Where are we at? As I said, the 3.2 is at committee draft stage. We just approved it. So if you get your hands on the spec, you can start implementing it. It should have been pushed off already. It hasn't been, so one of the things I need to do when I get back is find out from Oasis why it hasn't pushed out for public review yet. But it should show up in the next week or so. You can go to our GitHub repository and go grab the header files and start using the header files right away. We had 0 changes between the committee draft and the final draft in 3.1. We're expecting the same thing in 3.2 because basically most of the comments are, oh, we'll fix it in the next release. It's got to be something really, really problematic for us to not accept it. So the only changes will be like editorial changes that, oh, the spelling of this word was wrong or something like that in the spec. Mu support is going to be in 3.3, like I said, but we'll publish the particulars before that so that you'll be able to start using it. The Oasis process will probably get the final draft approved late next year, but you don't need to really wait for that. You can start working on the committee draft. So, in summary, don't implement the algorithms yourself. And PKCS 11 3.2 has all the primitives you need in order to implement your own PKCS 11 module, or as an application, use the PKCS 11 module and get standard PQ stuff. So with that, I'm a little ahead. Any questions? Everybody's ready to write PKCS 11 modules for post-quantum. OK, well, thank you.